So with this first one, we should recognise that 2p all to the power of 0 is equal to 1. Anything to the power of 0 is 1. The 6 gets raised to the power of negative 2. The p also p to the negative 1. So that multiplying those powers, that becomes p to the negative 2, leaving us with 6 squared, which is 36. And if we write this with a positive indice, that's got to be divided by p squared. With this next one, simplifying the left side, we get 4 divided by 2 is 2. A squared doesn't simplify. Then you've got b to the 6 divided by b, which is b to the power of 5. Now, because these are subtraction, our normal laws don't apply. We can only add or subtract here using like terms. So the term is 2a squared b5. Take 3a squared b5. So 2 subtract 3 is negative 1, and we cannot change that variable or those variables. With this one, negative 2 gets raised to the power of 4, so negative 2 to the power of 4 here, and then we've got h to the power of 4 and k to the power of 24, and that's divided by 32, and again that h squared gets raised to the power of 2, h to the 4 and k to the power of 6, 2 to the power of 4, negative 2 to the power of 4, so that becomes, to an even power, becomes positive 16, h to the 4, they cancel, or h to the 0, which is 1, so 16, and then you've got k, subtracting the powers here gives me k to the power of 18 divided by 32, and 16 divided by 32 is 1/2. So there's our final answer here. With this next one, just multiplying through when you've got an indice raised to a power initially, and similarly with that second denominator, a squared b to the power of 4, and then once we've done that, we can multiply across the top, a to the negative 3, b to the negative 6, c to the power of 5. So nothing can simplify here at this point. I'm just putting them in order, alphabetical order, and now we can subtract our powers. This becomes a to the power of negative 5, this becomes b to the power of negative 10, and we've got c squared. So we would write this with positive indices like so. With this next one, we start by removing the bracket. That becomes 4, or probably start by removing the bracket, although we could cancel the q squareds very quickly there. So I'd write that as 4p to the negative 4, and this 4 squared, sorry, and this is 5 squared p to the power of 6. Now when we divide, we should be inverting and multiplying, and we're missing a q here, I'm not sure why. So I would start with that. Just do your invert and multiply. You could do the bracket part first, up to you, but don't try and do both. Do one step at a time. So multiplying through like so, and then if we work out that 4 squared, we could work that out as 16 if we wanted to, and then we're timesing that by 5 cubed, p cubed, q cubed, and in the denominator we've got 5 squared. We've got times out. Now I'm purposely not working that out because I'm noticing equivalence with the 5s here, and then we've got a p to the 6, just trying to group the numbers together, which is why I did the times 8 first. Then p to the 6, we've got a p squared, and times by q to the negative 3. So now I would just simplify my numerator, 16 times 5 cubed, p to the negative 4, p cubed, so that's p to the negative 1, q cubed, and then in the denominator, I'm going to stick with the 8 and 5 squared, but I'll just swap the order so we can line these up probably more than anything else. P to the power of 6 times p squared should be p to the power of 8, and then this is q to the negative 3. Now you don't have to do this. You could have, particularly as this is a calc section, actually just worked out 16 times 5 cubed here, and similarly 5 squared times 8. Work them out on the calculator, and then simplified that fraction in that way. So my choice was to go like this, so then I can go 16 divided by 8 is 2, and so that part's 2, and then I've got this divided by this is 5. This makes it a bit easier. This becomes p to the power of negative 9, and this becomes q to the power of 6, and actually that's all divided by 1. Now just to finish off, because we want positive indices, that p to the negative 9 becomes p to the power of 9 in the denominator. With this next one, best thing to do here is to keep the bases the same and then equate the powers for these first two at least. So base is 5. Do not be afraid. You've got base is 5 here. The base is the same, so we add the powers. Add the powers when you've got the same base and multiplying. So negative x plus 2x. I guess we could write that as 5 to that power equals 5 to the power of 6. Not essential, that line. But then, because the bases are the same, negative x plus 2x, which is just x, equals 6. And we're done. Here you should recognise that 27 is 3 cubed. So we would write that as 3 to the negative 3. That just brings the 3 onto the numerator. And now, because the bases are the same, we can equate the powers. So this becomes 2x equals 1. So x must equal a half here. This one here, a little bit trickier, but very similar to the one above, where we've got to just use our index laws. The bases are all the same. The base is all 6. So the first thing I'm going to do is just write that as x squared. So that's 6 to the 2x times 6. And this becomes 6 to the 5x. And now I can go, that's 6 to the power of 1. So that becomes 6 to the 2x plus 1. Right side doesn't change, and then I can subtract the powers because we're dividing. The base is the same, so 2x plus 1 take 5x. So now I've got 6 to that power is 6 to the power of 13. So then I can equate the numerator, 2x, sorry, not the numerator, the powers, 2x plus 1 take 5x. So 2x take 5x is negative 3x plus 1, and that's got to equal 13. And then finishing off, a pretty simple equation in the end to solve. So the hard part with this one was actually to recognize that you had to keep the base the same. Index laws still apply, but this time we're manipulating the powers. But with all of these, you can see now this is the third one where the aim is to keep the base the same and then equate the powers, so then you can solve for the variable. Now this one is a little bit trickier because you don't have the same base. However, if you think about where that take 5 is, if we add 5 to both sides, we end up with this equaling 32. Now 32 should start to look familiar because 32 can be written as a base of 2 and the 4th can be written as a base of 2. So if we just get this into 1 by subtracting the powers here, 4 to the power of 7 taken, now 4 is 2 squared. And so suddenly now we have the scenario where the bases are the same and we multiply the powers here. So that becomes 2 to the power of 14 take 2n equals 2 to the power of 5. And so now we can equate those powers. 14 take 2n equals 5. So 14 take 5 must equal 2n. So 2n must equal 9 and then n must equal 9 on 2, or 4.5 if you prefer. Just finishing these last few off now. This one here, straight on the calculator. With question 14, again, using the 2 to 10 method might be helpful here. We want to know the proportion. So the proportion, which is basically how many died out of the total, I guess. How many died, which is the 5.5 times 10 to the 7 divided by the total. So again, you could use the 2 to 10 method. So the smallest number here, I'd make that a 2, that's a 10. And we want to know the proportion. Well, 2/10 of the people died. So 2/10 of the people died. So this divided by this, which ends up being, just using your calculator, nothing expected there. Otherwise, it's 0.6875. With this next one, again, you could use the 2 to 10 method, up to you. We've got 5 litres of blood, 40% of which are red blood cells. So the first thing we've got to do is work out 40%, which is 0.4 of 5, which is 2 litres of red blood cells. So each red blood cell has that many. So how many of those goes into 2 litres is really what we're looking for there. Now, you would expect this to be a pretty big number. So for those of you that got something like 10 to the negative 14, that tells you something's not quite right. That should be a plus 13. So that's a pretty big number, which you would expect because we've got a whole heap of red blood cells in the body. All right, the main error here is probably to recognise that you've got 1.8 metres squared is actually 1.8 times 100 squared, or 18,000 centimetres squared. And it comes from the fact that 1 metre squared, 1 metre, which is 100 centimetres by 100 centimetres. So 100 times 100 is where the 100 squared comes from. So that's the first thing you need to know. And then from there, 18,000 centimetres squared divided by the 1.13. So again, this time we're saying, well, how many of those goes into this number here? And again, a pretty big number.